I want to say a few words about Stefano Ermon's appearance at the Twimmel podcast. Shout out to Sam Charrington, always useful to listen to his interviews. So Ermon has been working on diffusion models for text for a couple of years now. And I think there's a couple of interesting things to say here. First, the fact that it works at all is pretty amazing. So I'm going to talk about how I think it works, or my understanding, and often just being able to explain something also helps me learn it. So I want to understand it because the key of diffusion is actually not for text, it's for video and image, which is, according to Elon Musk, the bulk of any kind of AI application in the future. It's going to be used for robotics at inference time, for training, and also media generation. And just if you think of AI as a bit stream problem, then the number of bit streams with 4 dimensions versus 1 dimension is just going to be much larger. So what is diffusion for text, right? The idea of diffusion for text is that you prompt an AI and then it generates a text based on the concept of diffusion. So it in one shot generates an answer to the prompt. It doesn't do it autoregressively, so it doesn't predict the next token. It predicts all the tokens relative to each other. Fundamentally, diffusion, the concept of diffusion comes from physics, and it has to do with the dissipation of heat and the denoising, being once you have a system which starts from a clear image and then gets to full noise, then you learn how the denoising works by going backwards. So the forward pass is denoising, and then the denoising is the backward pass, and you learn how to do that. So if you see a tree and then you turn it into a Gaussian noise, then you can denoise the tree back to roughly the same like it was before, sort of statistically relevant at least. So that's the idea. Now with text, the same idea applies to text because you can actually train the model in a similar way that you have lots and lots of text, millions and billions of pieces of text. Same way the GPT is trained. The architecture of training is slightly different, though. You're putting on you're kind of redacting the text, and you're training the model to, in one shot, de-redact the whole document. So you don't do next token prediction. You predict all the tokens and the bidirectional attention that applies to the tokens. Now, for text, this is a little bit more difficult than for images and video because there is less symmetry in principle. Although Ermon says there's actually not true, particularly in coding, there is actually a lot of structure in coding too. And you could actually look at a piece of code almost similar to a piece of image where there's a lot of symmetry to be used. And symmetry in physics means actually it's the opposite of matter. So symmetry is when everything is the same both ways. And when symmetry breaks, that's when information happens. So what diffusion really does, it predicts when symmetries break. So first you then don't have to predict every possible token. You only have to predict the tokens where symmetry breaks because that's where the information is. In other words, you have a blue sky and then all of a sudden a green tree, that's where the symmetry breaks. You don't have to predict the blue sky tokens until they break with the green tree. That's where the symmetry broke. So that's kind of the way I understand it. And in text, that's a little bit more difficult. So Ermon has found what he calls directed scoring function. So it just means that because in words, you don't have, when you predict words in one shot and the distribution of the words relative to the prompt, you don't have, the cat sits on a map. The word sit could have an infinite amount of possibilities in an infinite amount of sentences. But what you can do relative distribution, relative frequencies of words that come in the context that you're prompting. And that's kind of the directed scoring function that Ermon is using. I'm not going to go too much into technicals here. My main point here and the excitement that I get from this interview is actually a comment that Elon Musk made on November 25th, links in the show notes, and as an answer to Ermon's paper. And that is that he said eventually all bit streams are, he said bit streams are, diffusion can be applied to any bit stream, obviously. The word obviously is a little bit suspicious here. Why is that obvious? Well, if you think about it, a bit stream is zeros and ones, and it kind of every bit stream that has information has some sort of structure. So you should be, in principle, able to train that either through autoregressive or diffusion. And I'm going to talk about the advantages of diffusion in a second. But most importantly, he said that most of AI will be used for video and image analysis, and therefore diffusion will be a lot more applied. Now, that is something also Stefano Ermon is actually admitting, and even though his company, Inception Labs, is right now only working on text, eventually they're going to go multimodal. And when you think about multimodal applications for diffusion, then it starts making a lot of sense. And I think this comment by Musk is very important because you kind of have to think of Tesla, SpaceX, and X as a diffusion company, because the bulk of their applications will be real-world AI, and real-world AI is about video and images, mainly video actually, and also images, which is kind of, video is just images with the time dimension applied to it. So that's actually a useful way to think about the future of Tesla, SpaceX, and X, right? And that's also a differentiating factor. Real-world AI is heavily video-driven, and diffusion models will be used for training, they will be used for inference. And the advantage of diffusion models are, number one, latency is much faster, but also, and that's something that I'm not 100% sure about, I analyzed this a little bit more with Grok, but I think that you can also take a lot more advantage of compute because you can parallelize faster. So you do have a large memory budget, you do have a large compute budget, but you have a less flop per watt or solution per watt budget. And that's huge, of course, if you think about it in this day and age when everything is about, tokens per watt. You get more bang for the buck because you can use compute more efficiently. Now, everybody would attest that the memory wall is the fundamental problem in AI, that we have massive advancements of compute, but that the memory, and particularly also the memory, the IOs, are lagging the compute. So we have a lot of idleness on the compute side because memory is not fast enough or too expensive and so on and so forth. So what diffusion does, it kind of substitutes memory with parallelism. So it gives compute more prevalence thanks to parallelism. It does increase the cost of memory initially because you have to do more compute and you have to have more SRAM, for example. So something like the Grok, the acquisition that NVIDIA made, could be used for diffusion actually. But in the long run, particularly with large scale deployments and also long context windows, the high availability of compute and the ability to parallelize and still get very good results without having to rely too much on memory through parallelization could actually be an advantage. Now, this is not 100% clear. I have to do some more work, but I think this is the direction where things are going with real-world AI. Again, real-world AI being the AI that we care about. Coding is sort of midpoint here. So it's not real-world AI in the sense of FSD or Optimus, but it's real-world in the sense that it actually executes real or solves real problems in the real world that have physical consequences. A piece of code can, for example, activate something, or so you have, if you will, if power is the ability to move something, and code gives you power the same way FSD gives you power, or Optimus will give you power. So in that sense, code, and I think there is a case to be made that diffusion models work really well for code, because code has sort of an image symmetry type flavor to it. It's not a poem or a piece or a novel or something. It's a lot more structured, and the beginning and the end have a clear combination. Of course, there's many ways to write a piece of code, but the actual solution, still the solution space relative to all the possibilities of the words and symbols you can use is relatively limited. So in that sense, similar to an image where if you see an image of a blue sky and a tree, it's highly likely you're not going to see a dragon or Harry Potter on that same image. So to summarize, I think Stefano Ermon's work at Inception Labs is very inspiring for a couple of reasons. One is it shows how new architecture keep emerging. It also shows that diffusion in principle can work for any kind of bit stream. And most importantly, relative to what Musk said in November of 2025, that diffusion will be particularly useful for video and image. And since that is the main use case for real world AI, diffusion will actually dominate AI in the future. Thank you.